Hello, everyone. I want to discuss an easier way to determine the electric field components above a semi-infinite line of charge. This is one of the homework problems, and it involved a messy integral, and Patrick has, from classes, introduced a simpler way to view it that can avoid the messy integrations. I think it's an absolutely brilliant way to go about it. So let's discuss it. First of all, let's look at the infinitely long line of charge, and then we'll talk about the semi-infinitely long line of charge. Okay, so if I've got this line of charge, by using Gauss's law, we can quickly find the electric field anywhere around it. We draw a cylindrical Gaussian surface around this line of charge. The cylinder maps takes advantage of the symmetry of this line of charge. The electric field through the sides of the cylinder is zero because all of these horizontal components cancel each other out. So all along the line, for any horizontal component created by this piece of charge, it's going to be canceled out by the horizontal component of another, produced by another piece of charge somewhere down the line. The only thing that is left is these vertical, I shouldn't call them vertical, but as I've pictured it here, it's vertical or upward or downward components. They're actually, if you view the wire from the top, the electric field is going to point out radially. Okay, so look at Gauss's law, E dot dA. Because the electric field is constant along this side of the cylinder, you're a fixed distance away from all the charge, so you would expect the electric field to be constant, and there's only that component away from the line of charge, so the electric field is always going to be parallel to the area normal vector. Remember, the area normal vector is normal to the surface at all locations. So I can simplify this integral as just E times A, and by Gauss's law, that equals Q enclosed over epsilon naught. Well, what is the area of this surface? Well, it's 2 pi a, where a is the radius. So 2 pi a is the circumference, and then you multiply by the length of this cylinder, this cylindrical Gaussian surface. What is L? I don't know. Let's hope it cancels out, because I just kind of arbitrarily chose this length for the Gaussian surface. Okay, so I'll go over here and look at the charge enclosed. Well, the charge enclosed is just the linear charge distance, linear charge density enclosed by the cylinder of length L. And the L's cancel. And so you end up with electric field as 1 over 2 pi epsilon naught times lambda over A, where A is the radius of the cylinder. Lambda is the linear charge density. Or another way to think about it is A is the distance away, because that's really what we're getting at, right? We're trying to find the electric field at some distance away from the linear charge. That distance is A. Well, if I multiply this by 2 over 2, then I end up with 2 lambda over A divided by 1 over 4 pi epsilon naught, and that, of course, is just K. Okay, so that is the electric field from an infinitely long line of charge. And as we've noted earlier, this electric field is just equal to the y component, because there is no x component here. It all cancels out. I hope you found that easy enough. Now let's look at the semi-infinitely long line of charge. Here we're going to have to find, because it's semi-infinitely long, meaning the charge starts here right underneath the point of observation and extends to infinity. So it extends on like this. We're going to have y components and we're going to have x components, because there's nothing over here to cancel out all of the x components pointing toward the left. And we're going to find those x and y components individually. So we start with just from, the Coulomb's law type version of the electric field, where you find the electric field due to a bunch of point charges, dq, and then you sum up all those infinitely small point charges. So Ex is equal to k, the integral k dq over r squared times cosine of theta. The cosine of theta gives us the x component, where theta is that angle that's made from the drawing a line to the observation point to dq. we can now substitute in that r squared in this equation. R is the distance from the point of observation to the charge. Well, that's just equal to a squared plus x squared. That comes from the Pythagorean theorem. A is the distance this direction. X is the distance this direction. And cosine of theta, drawing this triangle here, cosine of theta is adjacent over hypotenuse, or x over the square root of a squared plus x squared. We combine all that stuff together, we end up with the integral from 0 to infinity of x over a squared plus x squared to the 3/2 power, and that's in the denominator, dx. We do the u substitution like we did in class. U equals a squared plus x squared. Du is equal to 2x dx. Divide through by 2. So that's where this 1/2 comes from. X dx is equal to du over 2. So put the du in. Move the 2 over there. I also change the limits from terms of x to terms of u. So when x equals 0, I just plug that into this formula here, and I get a squared. When x equals infinity, I get u equals infinity. So these limits have now been changed. Integrate using the power rule like you would normally do. Increase the exponent by 1, divide by the result. 2, 1/2, they cancel each other out. And the negative in the denominator here just flips the limits of integration. So I end up with k lambda times 1 over square root of a squared minus 1 over square root of infinity. 1 over infinity is 0. So that means the x component is k lambda over a. To find the y component, you do the exact same thing, except that you plug in sine of theta. That really makes things more complicated, because sine of theta is opposite over hypotenuse, which is a over a squared plus x squared to the 1/2. And now we have this integral that's not as nice anymore because I don't have the x in the numerator. It's hard to, get dx in terms of du now. So you have to do a kind of tough integral using a trig substitution, where x equals a tangent of theta, dx equals a secant squared of theta. Or, and this is where Patrick has pointed out an easier solution. You can note that when you derive this expression for EY, the only difference for the semi-infinite line of charge and the infinite line of charge is the limits of integration. So we have this function here, EY. And so this is being integrated, but if I look at the function, just the infinitesimal portion of the y component of the electric field, k lambda a over a squared plus x squared to the 3/2 power, it's symmetric around x equals 0. If you have a semi-infinite line of charge, you integrate from 0 to infinity. If you have an infinite line of charge, you integrate from negative infinity to positive infinity. Well, that's really helpful because we've already found what the result will be integrating from negative infinity to positive infinity. We did that on the first page with Gauss's law, and it was that easy expression. Remember that k2 lambda over a. So then if you want to find the y component of the electric field for a semi-infinite line of charge, you integrate from 0 to infinity, so you take half of what that total integration was. And that total integration, again, we found by Gauss's law. So we take 1/2 of this, and that would be the y component for a semi-infinite line of charge. Easy. We just avoided that messy integral. So looking at it again, given the infinite line of charge, all x components cancel, so E equals EY. We know that from Gauss's law, E equals EY equals K2 lambda over A. That comes from either applying Gauss's law or integrating that function between negative infinity and positive infinity. You get K2 lambda over A, the area under this curve from the function dEy of x. Now moving to the semi-infinite line of charge, we found the x component, doing our normal methods, but the y component is just half of this total. So it's equal to k lambda over a. So now we have our x and y components of the semi-infinite line of charge, and we didn't have to do a messy integral involving a trig substitution. Genius, right?